I'm looking at different types of rates of change, average rates of change and instantaneous rates of change. In a previous video, I looked at how to estimate average and instantaneous rate of change using an equation. Now I'd like to do an example in which I estimate average and instantaneous rates of change using a table of values, okay? So here's a table. I've got a time, let's say the time is in seconds, and I've got a distance, let's say that's in meters. And so, maybe I'm driving a radio-controlled car or something like that. We can see how many feet it's traveled after different times, okay? A table of values in an estimation is actually pretty important because in a lot of real-life scenarios, you're not actually going to have an equation that represents how something's moving. You're maybe just going to be watching something drive, and you'll note, oh, it's past this distance marker at this time, and it's past this other distance marker at this other time. And so this is a lot of these estimations. People sometimes say, well, this isn't doing real calculus because we're estimating these values. We're not actually calculating them. But in actuality, in many cases, the estimations are the only thing you'll be able to do. And on the AP exam, they will ask you to do these estimations. So these are literally things you will do on the AP exam in the first lesson of the year in calculus. All right, average rate of change, okay? Average rate of change is really just a slope from your starting point to your ending point. And so we're looking at the average rate of change over the entire interval between t equals 1 and t equals 10. Okay, so technically average rate of change is f of b minus f of a all over b minus a. In this particular case, actually, our function is function d, so it's going to be d of 10 minus d of 1 all over 10 minus 1. And we can just substitute all this in. Or if you want to think about it a different way, we're really just finding the slope between the point 1, 5 and the point 1032, okay? Just using function notation here, okay? So d of 10 is 32, d of 1 is 5, okay? And 10 minus 1 is 9, okay? On top here we get 27, and it's being divided by 9. By the way, if you put the units in these problems, if they give you units, a lot of times it's easy to figure out what you're actually finding here. This is a number of meters traveled. That's the displacement. That's how far this thing traveled. This is the number of seconds that have gone by. So our final answer is 3. We divided meters by seconds, so the unit is going to be meters per second. Anytime you're working with a rate, it should be the y unit divided by the x unit. Okay, so it should always be really easy, even if you're not sure what you're doing, to try to figure out what your rate is. Okay. By the way, if this had been a distance velocity graph, let's say that had been a v of t, and let's say this had been in meters per second. Okay, maybe it's speeding up. It's going 5 meters per second, then 13 meters per second, then 20 meters per second, and so on. If I found the rate of change here, the units would be different because I would have had meters per second in the numerator, and I would have been dividing by seconds in the denominator. And in that particular case, it would have been 3, you can write this 2 different ways. You could write this as 3 meters per second. And that's just basically saying for every second that goes by, this thing increases in velocity by 3 meters per second. Or meters per second divided by seconds. If you divide by a value, it's the same thing as multiplying by its reciprocal. You can write it as meters per second squared. Some of you might know from physics, the rate of change of the velocity, in other words, how fast your velocity is increasing or decreasing, that's called acceleration. Okay, so again, you could write it as meters per second or meters per second squared. But the point here is, even if you're not sure what the units should be, it's always the y unit divided by the x unit. Okay, let's go back to the original though. This is going to be d of t, and this is going to be in meters. Okay, let's look at instantaneous rate of change now. So again, we don't have the actual function. Okay, we can't do actual calculus with this. We're not going to be able to find the actual instantaneous rate of change. If you remember in other examples, we've picked points that were really, really close together. But this is a table. This is all we have, okay? You're never going to be asked to make up values or anything like that. So if I want to find the rate of change at t equals 3, I can't fabricate some value for what 3.1 would have been or what 2.9 would have been or something like that, okay? You just have to use the data you're given, okay? So the best we can do is pick a point that's very close to a time of 3, okay? 3 is 2 seconds away from 1. It's only 1 second away from 4. So honestly, using the 0.313 and the 0.420, it's probably about as accurate of a rate of change as we're going to get. And again, the instantaneous rate of change is trying to tell us what this is doing in exactly 3 seconds, okay? But just picking points together, that's really the best we can do here. So in this case, f of b minus f of a, that's 20 minus 13, divided by 4 minus 3. This is in meters, that's in seconds. So it changes a total of 7 meters in 1 second. We can say it's traveling at about 7 meters per second, okay? Now, technically, that's an average velocity in the interval between 3 and 4. But it still gives you a pretty good idea of how quickly something is moving. So we could say, hey, it's going about 7 meters per second there. Now, you could say, but I want to look and see what's happening before 3. Now, the problem here is that's farther back. That's 2 seconds back, so it's not going to be as accurate. But you could also run those numbers and find out what's the slope between the 0.15 and 313, okay? F of b minus f of a, 13 minus 5, divided by 3 minus 1. That's going to be 8 over 2, which is 4 meters per second. So in this time interval, it was traveling about 4 meters per second as it comes up to 3. And then it's kind of speeding up as it comes through here. And then by the time it gets to 4, it's going about 7 meters per second, okay? You could average the 4 and the 7, and you could say that it's about halfway between those two. I think that would be about 5.5 meters per second. Again, because that time interval is a little bigger than that time interval, you could argue that this estimation might actually be a little bit better, okay? There's not one way to do this. It's not perfect because we really don't have points that are very close. So some people like to pick a point above and a point below and average the two. Some people just like to find the 2 closest points they can get and just use those, okay? Both have good arguments. Neither one is necessarily totally right or totally wrong. But that's how you can use a table to find average rate of change and basically do the best that you can to try to estimate an instantaneous rate of change.